Now here's where we get to the heart of the Faraday effect. When we move a magnet through a conducting loop, we get a current flow. The direction of that current flow depends on the movement of the magnet. Saw that with the demo I did, and you can try it out on that PhET simulation for yourself if you wish. The direction of the current flow is summarized with Lenz's law, which says that there's an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in flux. What all that means is that nature doesn't like any change in a magnetic field, and nature will always create a new magnetic field in a direction to oppose whatever change it is that we're making. I think that's pretty cool. If you move a magnet around, nature doesn't like it, and it's going to make a new field to oppose that change. I think that's really cool. Lenz's law is a qualitative description of Faraday's effect. We're going to do some examples of that next. Then we're going to move on to a quantitative description with Faraday's law, and that gives us a tool to find the size of the induced currents.
Okay, let's apply Lenz's law and let's see if we can find the induced field and the induced current. If we take a magnet and we push the north pole of a magnet towards a conducting loop. So I'm going to model this. Here's my conducting loop. Here's my magnet. This is the north pole with the magnetic field lines coming out of it. So if I take my magnet and I push the magnet up towards the loop, it makes the magnetic field stronger. We're getting closer to the magnet, the field is stronger. Right off the bat, Lenz's law says that nature is going to induce a magnetic field that opposes that change. So if we make the field stronger pointing up, nature is going to induce a field that points down. Okay, that's the answer to what is the induced field. So let's draw that guy. The induced field is going to come down. So that's B. What kind of a current does that correspond to? Well, we're going to have to use our right-hand rule here for this. So our magnetic field points down. What you do is you make a circle with your fingers, and your fingers have to correspond to the magnetic field. Your thumb corresponds to the direction of the current. So I'm going to take my loop and I'm going to put my fingers down in through the middle of the loop because that's what we know the induced field is. Then I ask, what is my thumb doing on that front edge of the loop? So I put my hand down through the middle and my thumb is pointing this way. So that's the direction of the induced current. So we'll grab a different color. Induced current comes around the loop to the left in front. So there's the induced current. So that's how you work out those problems. You figure out what's the change in field and how does that correspond to the induced current. Okay, I think we can probably do this one a little faster. Still have our loop and our magnet, but this time we're going to pull our loop away from the magnet. So we pull it up away. First thing you ask is that motion of the loop, what does that do to the field? We're getting further away from the magnet. There's a weaker field. Nature doesn't like the field getting weaker. It wants the field to stay strong. So the induced magnetic field is going to point in this direction so that it stays strong. So we made it weaker. Nature doesn't want it to be weaker. It still wants a big field pointing up. So we induce more field pointing up. Now let's ask, what does that mean about the induced current? We know that the induced magnetic field points up, so we take a circle and we curve our fingers so that they point up. Then we ask, what is our thumb doing on the front of the loop? Our thumb is moving this way, so that's the direction of the induced current. Let's draw that on our picture. So there's the induced current, and this was our induced field. This one is kind of a neat example because our loop first falls sort of in free space with no magnetic field. Then it falls to a region with magnetic field, and then it's going to leave that and fall in a region with no magnetic field. So let's think about what happens at each one of these stages. So first, while the loop is falling in free space with no fields, there's no change in magnetic field. that loop is always in a region with no field. If there's no change in field, there's no induced magnetic field and no induced current. Okay, the interesting stuff happens next when that leading edge hits the top of the magnetic field. Okay, this picture shows us into our next phase. The leading edge now has entered the magnetic field and the top edge is out. So this is in and this is out. So what this means is as our leading edge reaches the field, we've gone from a region with no magnetic field into a region with field into the page. So as it drops, it goes into a region where field points into the page. Nature doesn't like that. It doesn't like that we've put field into the page. So it will create a new field that points out of the page. Okay, so the induced magnetic field is going to be out of the page. There's our B induced. What does that mean about the current? Well, we have to use our right-hand rule. We'll make a circle with our hands representing the magnetic field. We see that our fingers are pointing out of the page. We put our fingers in the middle of that loop because that's where the field is, in the middle of the loop, and then we ask, what is our thumb doing? So our thumb is pointing this way. That's the direction of the current. So our induced current comes around this way. You might think, I won't draw it here, but you might wonder what is the direction of the induced magnetic force in this case. Our next phase of the problem is after the top edge has entered the field and before the bottom edge has left the field. So always within the field. So always, I'll even add in the word completely. So all of the loop is in all of the field all of the time. If the whole loop is in the field all the time and that field is constant, then there's no change in field. That means no induced magnetic field and no induced current. Okay, that's kind of interesting. As the loop falls into the field, we get an induced current. Once it's fully in the field, the current goes away. Next question is what happens as the top edge, as the bottom edge reaches the bottom part of the field and it starts to leave the field. Almost done with this example now. So now the top edge is still in the field. Bottom edge is out of the field. So our loop is now leaving an area where magnetic field points into the page. So what's happening is that we're actually decreasing the amount of field into the page. So here there's field into the page. Now there's less field into the page. Nature doesn't like that change. It wants it to keep that field into the page all the time. So nature is going to create a field that points into the page. So we'll take our fingers and we'll make a circle with our fingers that point inwards. We'll imagine we're grabbing the bottom of that loop, asking what our thumb is doing. So our thumb points this way. That means that's the direction of the induced current. Okay, let's draw that in our picture. So our induced field is into the page to make up for the fact that we're leaving the field. And then that corresponds to an induced current that comes around this way. So there's our induced current that's coming around clockwise. And again, I'd invite you to ask yourself, what's the direction of the magnetic force in this part? Okay, last little bit is after the entire thing is out of the field. Now the loop has completely fallen out of the field. So it's in a region with no magnetic field at all. If there's no field, there's no change. Therefore, no induced B or I. Just like when it was at the top before it entered the field. Here's another example. This one is a little different than anything else we've done so far. So we have a long straight wire, it's carrying current upwards, and we have a loop next to it. And the question is, the current in the straight wire is decreasing. What happens to what current is induced in the loop? So let's think about the fact that this is a current carrying wire. We know what makes magnetic field. The place we care about the magnetic field is in the loop. So let's ask what magnetic field is made in the loop by this wire. You know that the magnetic field makes big circles around the wire. The circles either go this way or this way. To know which way, you use your right-hand rule. Put your thumb with your current, and your curled fingers show the direction of the magnetic field. So I'm taking my fingers and I'm curling them around until I'm in the middle of my loop. What I see happening is that where the loop is, the magnetic field is going into the page. I'll draw that in my picture. So there's the magnetic field due to the wire. Okay, now what happens to that magnetic field? The current in the straight wire is decreasing. We know that B is mu naught times I over 2 pi r, where r is the distance from the wire. If the current decreases, the magnetic field strength also decreases. So the change in the magnetic field is that the field which pushes into the page is getting smaller. Nature doesn't like any change in field, so it will create a new field so that that doesn't change. So if into the page is getting smaller, nature doesn't want it to get smaller. It's going to create a new field that points into the page to try and maintain that field. So the induced magnetic field is into the page. What does that mean about the direction of current? Because that's what we're asked for. So the induced magnetic field is into the page. You make a circle with your fingers, and you have to make your fingers match the magnetic field. So my fingers need to go into the middle of the loop. Now I ask, what is my thumb doing? So I'll ask, what is it doing on this side of the loop? I see right here on this side of the loop, my fingers are going up. On this side of the loop, my thumb is going down. So here, my current, my thumb goes up. Here, my current, my thumb goes down. That shows me the direction of the current. So let's draw that on the picture. So there's my current. So it flows around the loop this way. That's a clockwise direction. So I induced is clockwise. So you're always asking, what is the change in the field? How do I counteract that change with a new field? And how does that correspond to the induced current? This is another example that looks a little different, but operates on the same principles. We have two loops, and the lower loop is connected to a source of potential. When we close the switch, we're going to ask what happens to the upper loop. So we close the switch, it means current is allowed to flow. So current comes out of the battery in this direction, comes around, and I know this is a 3D picture, not the easiest to see. So it comes around and back in this direction and around in front in this direction. We know that current carrying wires will create a magnetic field. So here are my two loops. What happens with the bottom loop? So the current comes around this way in the back and this way in the front. I'll point my thumb in the direction of current in the back, and I'll make a circle with my fingers. So my thumb goes with the circuit, goes with the current, and my curled fingers are pointing upwards. So when I turn on that loop, I create a magnetic field that points up. So this magnetic field is created as soon as I flip the switch. So that's B from the lower wire. Now what happens? So what I've done is I've created a magnetic field that points upwards through this top loop. Nature doesn't like that change in the field. Nature is going to make a new field to counteract it. What would be the direction of that field? That would have to be down. So if we make a field that points up, nature is going to induce a field that points down. So the induced field is going to point down, be induced. Okay, what does that mean about the current in our top loop? So I'm going to use my right hand rule. I'll make a circle with my fingers, and I see that my fingers point down through the loop. So in the back of the loop, my current is coming this way. Around front of the loop, it's coming this way. Let's draw that on the picture. So there's my eye in the front. There's my eye in the back. What you can see here is that those currents are in opposite directions. Now, the specific question is, does the lower loop exert a force on the upper loop? So let's recall what we did in an earlier lecture. Two current carrying wires do indeed experience forces between them. If the wires carry current in the same direction, the force is attractive. If the wires carry current in opposite directions, the force is repulsive. So what would happen is that that top ring would experience a magnetic force that goes straight upwards. I scooted over to the university to make a video of my favorite Faraday effect demo for you. Here's a pretty neat Faraday's law demo. What I have here is a solenoid. So we have some coils of wire here. We've got a solid iron core, and I can turn it off and on. Right now it's turned off. I'm going to take a little aluminum ring and I'm going to put it on top of the core. So it's turned off, nothing's happening. I'm going to turn it on. What do you think is going to happen? Okay, so anybody who guessed it was going to fly off would be absolutely correct. Let's do that once more in case it went by too fast. So what happens is a Faraday's law effect. We put this here, we turn on the solenoid, it creates a magnetic field that induces a field here, which induces a current. Now we have a current carrying loop in a field. It experiences a magnetic force. That force is what makes it fly off. Okay, why don't we do it one more time? We've got a different loop. Oh, I just turned it on, but it didn't fly off. Can you think of why not? While you're thinking about it, I'm going to bring the loop in close. See the difference now? So here's the loop that did fly off. Here's the loop that wouldn't fly off. The loop that wouldn't fly off actually has a gap in it, so current can't flow in this loop. I think that's a pretty neat demo. It shows that if you create a magnetic field, it will induce a new field, which induces a new current, which experiences a force, but you got to be able to let the current flow.